Hello everyone, my name is Kamal Human. Welcome to this lecture on hydraulic connections and heat exchangers. The goal of this video is to introduce to you heat exchangers and how to analyze them. We will see the basics we need to know and what we can and cannot with the heat exchangers. For instance, there always are resistances against transfer of heat and fluid flow. We have noticed pressure drop, for example. Some of these limitations are inherently unavoidable, as we will see in this video. Let's begin with a heat exchanger and what a heat exchanger is. Here I've got two photos, one of them taken from my charcoal barbecue at home and the other one from a water to air heat exchanger in my office. In both of them, heat is transferred to air. With the radiator, however, we would notice a control valve that regulates the hot water flow rate. If we fully open the valve, we expect the maximum heat transfer from hot water to air around the heater. And of course, if we shut the valve off, there would be no flow of water and no heat transfer. If we assume that there is no heat is lost, then the numerical value of enthalpy change in hot and cold fluid streams must be the same. For air and water, in the absence of phase change, you'd remember that the enthalpy is a linear function of the temperature difference. So we're left with an equation that relates the average inlet and outlet temperatures of two streams to each other. For an existing heat exchanger, like the one in my office, sizes are fixed. The duty of heat exchanger is usually prescribed, and we can calculate the air or water temperature if we have enough information. That is, we'd rate the heat exchanger. However, if we were told that we need a set heating duty and the room temperature has to be within a given range, then we could design a heat exchanger or we could size it in a way. Usually, with sizing problems, we have some degrees of freedom, and a number of parameters will affect our design, including those shown on the slide. Design parameters will affect the performance of a heat exchanger. We remember from thermodynamics that all the processes are irreversible in nature and that always are losses which would lead to destruction of exergy. For heat exchangers, we have to deal with thermal resistances as well as flow resistances. The simplest way to explain is to think about a metal or a wood spoon in kitchen. They both show resistance to conduction heat transfer, but we expect it to be easier for metal to conduct the heat transfer. You have also seen in your fluid mechanics course that a pressure drop through rough pipe is higher than that of smooth ones. Also, we've learned that we need to push the air harder to overcome flow resistances. This translates into pumping power consumption, which is linearly proportional to fluid pressure drop and flow rate. But what are the sources of flow resistances? Some are shown in this slide. For instance, if you go back to heat exchanger in my office, the valve that controls the flow rate imposes resistance against the flow. Even without the valve, flow in a straight pipe induces frictional resistances or losses, as you have seen in your previous courses. If the pipe is not straight, then a bend, for example, can add to flow resistance. But how do we account for these minor and major losses? One way is to rely on graphs which relate the irreversible dynamic pressure to the actual pressure drop through a friction factor F or K. The graph to the right, for example, shows the friction factor, or F, for flow in a pipe versus Reynolds number on the x-axis and F on the y-axis for different flow conditions. Whether the flow is transitional, turbulent, or laminar flow, the pipe is rough or smooth. For different roughness heights, we could have the friction factor. Design of heat exchangers and hydraulic connections are governed by codes and standards, some of which are shown here. Guidelines are available and are prepared in response to practical limitations, some of which are presented here. To recap, we have seen an introduction to what heat exchangers are and how they operate. We have also covered how we can rate or size a heat exchanger using fluids or heat rates to limitations within the system.